सैंदनी, गुड इवनिंग।
गुड इवनिंग सर।
अच्छा, कुछ मैं बोल रहा था, कुछ इम्प्रूवमेंट फायदा हो रहा है एनएलपी क्लास में? जो भी
यस सर।
क्लासेस हम लोग सोच रहे हैं इसको कैसे आगे बढ़ाएंगे, किस अप टू रिसर्च प्रोजेक्ट लेवल तक लेके जाएंगे, so that we can get some research project as well as we go for the publications. बट रियल लाइफ प्रॉब्लम जो है, रियल वर्ल्ड प्रॉब्लम, उसको ही लेके हम लोग जाएंगे आगे। देखते हैं, बहुत कम स्टूडेंट अभी ज्वाइन कर रहे हैं, तो उसके बाद हम लोग देखते हैं हाउ वी आर गोइंग टू सिलेक्ट सम ऑफ द स्टूडेंट्स फ्रॉम यू।
ओके
तो
सर।
इस तो मैं इसलिए देखा, बेसिक्स पहले क्लियर हो जाने के बाद देन, जैसे कि वर्कशॉप हमारा है जहाँ पे 15 रिसोर्स पर्सन आर ज्वाइनिंग एंड यू आर आल्सो गोइंग टू ज्वाइन देयर। ओके, सो वहाँ पे क्या होगा, वो लोग का पास प्रॉब्लम स्टेटमेंट है, दे आर वर्किंग ऑन दैट वन। लाइक एक मैम है, सुनन्या मैम, हु इज द माइक्रोसॉफ्ट रिसर्चर, प्रिंसिपल रिसर्चर इन माइक्रोसॉफ्ट रिसर्च इंडिया। तो वो लोग काम कर रहे हैं लो रिसर्च लैंग्वेज में। सो फ्रॉम देम ऑल्सो वी आर गोइंग टू गेट मेनी थिंग्स। लाइक एनआईटी का डीन ज्वाइन कर रहे हैं सिलेक्चर का, तो वो भी लो रिसोर्स में काम कर रहे हैं। तो मैं ऐसे लोग को साथ में से कॉन्टेक्ट किया हूँ जो लोग लो रिसोर्स में काम कर रहे हैं, एंड दे आर गोइंग टू शो द सेम थिंग। लाइक श्रीलंका से एक मैम है, पोर्तुगाल से एक अफ्रीकन, जैसे अफ्रीकन लैंग्वेज में काम कर रहे हैं, शमसुद्दीन है पोर्तुगाल से। फिनलैंड में एक सर है जो कि उड़िया का ऊपर काम कर रहे हैं, उड़िया जेनेटिव है। तो मुझे लग रहा है कि हमारा जो वर्कशॉप होगा उससे बहुत इनपुट हम लोग को मिलेगा। तो यू पीपल ऑल्सो बी सीरियस। तो प्रॉब्लम स्टेटमेंट बहुत सारा निकलेगा, और वी कैन कंटिन्यू अप टू 6 मंथ। जो लोग काम करेंगे थ्रू आउट द ईयर वी कैन वर्क, नो प्रॉब्लम। तो ये मैं थोड़ा सर को बोल देता हूँ, ज्वाइन करेंगे, भूल गया हूँ इसे। हेलो।
Sir,
हाँ, सो यू कैन you
okay.
can start, eh? I've already
Yes,
made
sir.
you the co-host. I'll join after 30 to 40 minutes. Eh?
Yes, sir. Yes.
Recording I have already started. You can continue. Huh? Bye.
Okay. Let me share my screen. Yes. Is it visible?
Yes, sir, it is visible.
Okay. Okay. So, so today what we'll do, actually I have planned to discuss what to make, but I defer it for the next session because some other concepts of neural network which is required there need to be understood first. And also today what we'll do, we'll discuss all those extra concepts which is required for training a good neural network in any platform or any framework. And also we'll implement the same classification last session what we have done, but in text. So previously we have done it in numbers, but here we'll do one text classification using simple neural network and see what will be what is the outcome and how we can improve it. In the next class we will discuss how to improve it. Okay. So today my topic of discussion are these things. Okay. One is mini batch stochastic gradient descent. They are the important concepts. By the way, just try to understand the concepts and how we'll implement in code, that also we'll discuss. Some all will not discuss. Some of the which are very important, that we'll discuss. Mini batch stochastic gradient descent, importance of learning rate, dealing with local minima, popular activation functions, weight initialization methods, feature scaling methods, regularization techniques, and last we'll see what is the deep learning. Okay, so let's start. So let's see what is batch gradient descent. In the last session what we have discussed, that how we are training a model. So we have created a network. This is my network, which has some inputs and here hidden layer and some output. Okay. So now my question is how we are actually training. So we are training how, you just see that we have the data set. The data set is converted into numeric form. Let's say this data set has four features: x1, x2, x3, x4, and each row represents one data point. Okay, and let's say I put everything in this matrix, let's say I have 100 data points, 100 such data points available in my training set. Now all 100 data point each has four features. These are the four values for each data point. Now what actually we are doing during training, we are passing one by one all the data points, and after passing that, the gradient will be calculated backward. During gradient calculation and back propagation, the data, the weights are updated, and in this way we are learning. But generally what happens, instead of giving one by one in a batch gradient descent, which is very common, that the updation is actually not happening after each data point which is passing through the forward pass and backward pass. Rather, what it does, data points in the data set, once it is passed through the forward pass, and again all data points, their gradients has been calculated, and overall gradient will be used to update the parameter values, that is the WH. That means all data point is required to update the parameter values. Call this as batch gradient descent. Batch means whole set of data points which are there in the data set are first passed through. It is just passed through the network in each iteration, and when it goes backward during back propagation, the gradients are updated and you got the new gradient. That means for one set of gradient update, or for first or one gradient update, all data points in the data set must pass through the network. So this is the best possible way, and it will give you good result. Okay, but what is the downside? There are two basic downside. One is slower. It becomes slower because you see, if you have 1 lakh data points, for only one updation of the parameters or the W values or the weights, you need to pass all 1 lakh data points. Once it is passed through all 1 lakh data points, and then only you can update it. So it is time taking. And also another important drawback is that if, let's say, you have 1 lakh data points, but your memory is not sufficient to hold it. Okay, so if your memory is not holding, then what will be the problem? So the problem will be that all the data points cannot be processed. Try to understand. So what I'm saying here, that once you have the data set, all data sets should be passed through the network, then only one gradient update step will be calculated. And this process is called batch gradient descent. And what is the problem with this? The problem is that it will have slower feedback, because for one updation you need to pass all the data points in the data set. And another problem is that if your memory is not sufficient to hold all the data points, then you cannot pass it. So if your memory, your data set requires 1 GB of memory, means I'm talking about RAM. So, and you do not have that 1 GB of RAM, let's say, is not available for the time being, then all the data points cannot be loaded in the memory. Then only once it is loaded, then only it can be passed through the network, but it cannot do that. So this is the problem. Now, what is the alternate solution? The alternate solution is called stochastic gradient descent. Here, stochastic means instead of passing all the data points to update one set of parameters, or for one updation, instead of passing all the data points, we can pass only one data point. That means you just randomly sample one data point from the data set, pass through this network, then update it. That means for one iteration, instead of passing all data points to update it, you just pass any one data point. It will go through this network, and it will again come back as the feed forward in the back propagation, and during back propagation, it is going to update each parameter in the network. Again, in the next iteration, you select another sample, and again it will go in the forward pass, and during back propagation, again it will update. That means your updation will be faster. After each input, means after each selection of each data point, the updation will be done. Instead of waiting for the whole data to process to update once, you need only one data point to update. Okay, and what is the good way of doing? What is the advantage of that? Now it will be have quicker. So if you want to update it quicker, the data, the parameter need to update it quicker. So you need not to wait for the whole data set to be processed. Rather, you select one data point, process it, and you will update the parameter. And also for memory issue, that also solved, that we do not need to hold all the data point in the memory. Rather, we have only one data point. You just can load in the memory, and from the memory it can calculate the forward pass and backward pass and also update it. So it also avoid loading all data in the memory. But what is the problem? So the problem with SGD is that it has erratic convergence path. The convergence path to the minimum is not that smooth. Just see, let's say this is the top view of your loss surface, and if you use, that means here we have two parameters, W1 and W2, or they are the two weights. This is the minimum. W1 needs to be here, W2 value needs to be here. So if you use batch gradient descent, after each iteration it will be updated like this and you will reach the minimum. So you see the path is very smooth, it will converge smoothly. But if you use SGD, you see SGD is harder to converge, because after each input or after every single data point you are updating, so the updation will be have this erratic behavior. It will jump here and there, and after many times it may not converge here, but also it can overshoot it. Okay, so this is the problem with SGD. Is it clear? So with batch gradient descent, whole data point need to be passed through the network in order to update once the parameter, which is very costly. And if you do not have that much memory to hold the data points, so it will be also difficult. So solution is you use stochastic gradient descent instead of batch gradient descent. Stochastic gradient descent says that without using whole data point, rather you use only one data point, pass through the network and update the parameters. Okay, but it has a problem. What is the problem? Problem is that it is not smooth. The convergence is not smooth. But we cannot go to the batch gradient descent. Why? Because we may not have the memory. So what is the intermediate solution? So the intermediate solution is neither go for the whole set of data point, nor you go for only one data point for one updation. Rather, you create a mini batch. So we call this idea as a mini batch stochastic gradient descent. So it is very common in the practice that nobody uses whole data set to update the parameters. Rather, all are using batch, mini batch. What is mini batch? So the concept is very simple. Here, instead of sampling only one data point, rather you sample a multiple data points. Means let's say 3 or 4 or 32 number of data points from the data set at each iteration. So you select some of the data point, we call it as a mini batch. Then you pass all these selected data point through the network and then update. Okay, so this will be little bit slower than the stochastic gradient, but also faster than the whole batch gradient. And also the memory is not that much required as it is required for the batch gradient. Okay, so it takes the advantage of hardware, that is matrix operation, hardware matrix operation we are doing. Also, it has less erratic convergence. It will have some here and there convergence will be, there is a little bit problem. It is not that much smooth, but still it is not that much erratic like you are seeing in the SGD. Okay, so how we'll create the mini batch? Let's say these are the data points available. Let's say there are 6 data points available. What you do? So instead of sampling at the time of training, rather you do it beforehand. What will do? Now you just shuffle the data point and split them into batches. So let's say my batch size is 3. So what you will do? Now you shuffle them so that a good mixture randomization will be there, so that there will be no bias. And here we are taking 3 let's say my batch size is 3, so we are converting the whole data set into number of batches. Each batch contains a number of data points, let's say 3. Now what you will do, you pass first batch, then it will go through the network, and when during back propagation it will update once parameter. Next, it will update the weight. Next, it will take another batch. All the data point in that batch will pass through the your network, and during back propagation it will update it. So your updation will be faster than batch gradient, and also it has less erratic behavior than the stochastic gradient. So this is the best practice people are using. Okay. So question is, how large will be your batch size? So that depends on your requirement, means on your hardware, means let's say your memory. And the general idea is that the batch size is generally between 32 and 512. So general 32 is very popular. You can also take 16 if your data is very means one data point is very large, and if you take a 32 as a batch size and it cannot hold in your memory, also you can reduce it. Generally, the convention is always you take something 2 to the power something. So it can be 4, 6, sorry, 4, 8, 16, 32, and like this. But general convention is 32. Okay. So you first start with 32. Otherwise, you go, means let's take bigger batch size. So this is called the batch gradient descent, or rather we call it as a mini batch gradient descent. So this mini batch gradient descent is actually being used in practice. So when we'll deal with the means when we'll train it, so before giving the whole data set to the data to the model, rather you create batches. So batch by batch data will be giving to the model. Okay, is it clear? Next is learning rate. So first thing is clear that what is batch gradient descent, how we will deal with that. Next is learning rate. Let's say how we'll find effective learning rate. We know that in every gradient descent there is a updation step. What is the updation step? Already we know this. This you have to remember, because this is the golden rule of your deep learning or your advanced learning. What it is? It is the updated weight or new weight equal to the current weight or the old weight minus this alpha is your learning rate and the gradient with respect to that W or that parameter. Okay. So here this learning rate is a hyper parameter that the user has to provide. Now the question is how we will decide what will be the best learning rate or effective learning rate for my data set to be trained on a particular model. Okay. So this is our question. How we'll deal with that? Let's see. So let's say this is my cost function. Okay, this is my parameter W, and this is my loss or cost, both are same. And this is my surface or my cost curve. Okay, so if you take a small learning rate, let's say learning rate is very small. Generally, learning rate is between 0 and 1. If you take a very small, let's say 0.000001. So what will happen? And the updation will be very slow. If this fast circle is my initial guess, then after updation it will come to just a little far. So the updation will be very slow and it will take time to reach.
Naran sir, you are not audible. Am I audible, students?
Yes, sir.
Yes,
Okay,
sir.
I think some network issue there. Rain is outside there.
So let me share it again. Is it audible?
Yes, sir.
So okay. So what I am saying here, that if you take the alpha or the learning rate very small, then your updation will be very slow. It will take time to reach this minimum. Okay, so it takes a long time to converge, and sometimes it will won't come means to this due to your computational limit. If your computational limit will gone, then you cannot come to the minimum. But if you take the learning rate very big or too high, what it will be? It will oscillate like this. It will oscillate here and there. It will never come to the minimum. So it may overshoot, bounce around. Okay, we call it as oscillation. So it will oscillate and it will not come to the minimum. So this is the problem. So that's why choosing a best learning rate or effective learning rate is most important for convergence to the minimum. Okay. So let's see. So what we need? We do not need this slow. We do not need the that we cannot go to the minimum. So we need a balance between them. So how will get that effective learning rate? So there are different ways to do that. One way is that called hyperparameter search techniques. One such technique already there in ML, we call it as grid search. What is grid search? A very simple idea. Grid search is that what you do, you create a bunch of learning rate. Let's say I need between 0 and 1. Let's say I have created 1, but it is laborious and time consuming. Imagine you have created a list of 100 such learning rates, and you need to search which one out of these 100 is best for my model. So what you have to do, you have to means you have to create you have to go through the model for every learning rate and find out which one is best. Okay, but there is another alternate way to do that. That is called random search. Instead of giving explicitly the set of learning rate, rather what you do, you give the learning rate between one lower value and one upper value, and you randomly sample between these two values. Let's say I say my learning rate may be between 0.1 and 0.3. Okay, so and you create give a random function. So random function will select any one value between this. Let's say I am selecting almost only five or six values. So accordingly, it will calculate the same process is same. But here random search is going to be used. So it tends to find good combination with fewer tries. Okay, so this is one way you can find out what will be my effective learning rate. But there is other ways also available. What are they? Now you can use a learning rate scheduler. So sometimes what happens now, for some iteration, one learning rate will be better, but some other iteration, another learning rate may be better. If you fix the learning rate at the beginning and you pass through this model with the same learning rate again and again for every iteration, it may not be good. So we have something called learning rate scheduler. Okay, so that means you start with some learning rate, then reduce it over the iteration. It is not going to be fixed, and this is the best practice. Okay, how will do that? Now you can use exponential decay. So what we'll do, instead of using only the learning rate alpha, instead of using only the learning rate alpha, rather what we'll do, we'll use alpha e to the power minus dt. So here d is a decay factor, t is the number of iteration. For every iteration, depending on this d value, your learning rate is going to be decreased. Okay, and that will be best. Okay, this is one way. Another way that you can use piecewise constant decay. So instead of exponential decay, you can set that for let's say for my iteration 1 to 5, this will be my learning rate. For iteration 6 to 8, this will be my learning rate. So this is called a piecewise constant decay. This is another way to get. So these are the two common methods that is being used to create a learning rate scheduler for my learning. Okay, and another one is called one cycle policy. Here, what is one cycle? You increase the learning rate linearly for certain number of steps, then you decrease. This is another one. So also there are other variations are there, but these two or three are very common in practice. Okay. Now, if you see another concept, let's see. Generally, your loss function till now, what we have discussed, are a convex function like this, very smooth convex function. If your loss function is convex, then it is easier to get the minimum. Okay, but imagine that if your loss function is like this, it is not smooth convex, rather it is a non-convex function. I am not saying it is a concave, rather it is a non-convex. So in non-convex function, what happens? Now there are many minimums. This is called global minimum, and these two are called local minimum. Sometimes what will happen, now if your model is initialized here, somewhere here, then what will happen? Now when you go on doing the gradient descent, you may stuck at the local minimums, you may not come to your global minimum. So that is another problem. That is called local minima problem. Okay. So if you are here, if your loss function will start from here, then it will only go and stop here in the local minimum, and it cannot come to this global minimum. So actually we need this global minimum. Okay, but sometimes the loss landscape is very complex. If you see, this is a loss landscape represented for BGG 56. It is a model. It is a image net model. So BGG 66, you see, very difficult to find out the global minimum. There are lots of local minimum. Okay. So what is the solution? So how will escape the local minima? So let's say some of the solutions. One way that you can use SGD instead of using gradient batch gradient descent or mini batch gradient descent. You can use SGD because we know that SGD can jerk here and there. So there is a chance that during that jerk it can come out of this small hill, and again it will go to this when once it comes out here, then it can come to the minimum here. Okay, so this is one way. Another way is that you can use learning schedules, like we have discussed. You use learning schedules. If you stock here, you increase the learning rate so that it can come out of this loop of this hill, and it will be going to the global minimum. Okay, so this is the process that we can use for escaping the local minimum. Also another approach is that you can randomly start. Suppose you start from
Answer not audible.
so what we can do here, we can add a momentum. So in momentum, what we'll do?
Please
Nonsense.
share your screen.
Share the screen again.
Okay.
You are not audible, actually, no network issue. Anyway, you just share the screen again.
It's now visible.
Yes.
Okay. So what I'm saying, that how will come out of the local minimum. So one is how will escape. Now one again I'm going back. One is you can use SGD. So there is a chance that it can jerk out from this local minimum and go towards global minimum. Another one is you can use learning scheduler. So if you stop with the local minimum, increase the learning rate so that you can jump out of this and go to the global minimum. There is another option is that instead of doing that, you start with some initialization. If you are stuck with the local minimum, discard that, again you initialize somewhere. So if by chance you initialized here, then you can go to the or come to the global minimum. There is also other options. What is the other option? Now this is most most structured approach, that you can add a momentum. What is momentum? Momentum means instead of using simple updation, what this is the simple updation, gradient updation. That is a new weight equal to old weight minus learning rate into the gradient. So this is the plain gradient descent. But I want that this updation will be faster. That means this value, if it is if we are adding some momentum here, so the updation will be faster and it will come out of the local minimum. Let's see how we are doing. So here it does not care about past gradients. Now imagine that when we are updating the current in the current time step, when we are updating the parameter, we are only considering the current gradient, whatever is calculated at that time. Previous gradient which have already calculated and used in the previous updates, that we are not using. So if we can use that past gradient, then we can create a momentum value which will be added here so that it can update faster. So let's see. So so what we will do, we can use momentum which takes past gradient into account. So that momentum value m, how we will calculate, that is beta into m minus alpha delta. This is already there. Only I have what I have done, I have used previous gradients. So what is this? This beta is called friction coefficient. Generally its value is taken as 0.9. This m initialized with 0, but after that, after every update or every gradient calculation in every step, the m value will be accumulated. Okay. and that m value is being used for updation. So here what we are doing, now the new weight equal to old weight plus this momentum value. So now it has a momentum added with that, so that it can come out from the local minimum and go to the global minimum. So this is another approach. Okay. Now, if you see how momentum helps, so this one already we have discussed. So if you have a simple gradient descent, so if you initialize with 0.5, after so many steps, you will reach here. Okay, but if you use your momentum, let's see what happens. So after, let's say here, after 4 steps in general or plain gradient descent, your parameter value will be here in with this arrow. Okay, but if you use a momentum, here we are using momentum. Now initialized here, after calculation, it will come to directly with momentum. It will come to this place. After the second iteration, because you see this is the larger weight change, so you come directly here. So after 3 iteration, you are already surpassing the previous simple gradient descent. So momentum can help us to go quickly towards the minimum. Okay, and after 4 iteration, you are already close, very close with the minimum. Okay, so this is another approach. So here you see, if you add momentum, what happens without momentum? If we are using SGD, so this is my steps, means zigzag path, and then you will go to the minimum. But if you use momentum, quickly you can go to the minimum, so that the convergence will be faster. So this is another approach. Okay. And alternative approach is you just dampen the oscillation for a given weight. This is another way. So here you, but these are the things. But one thing you just remember, even if you don't do anything to come out of the local minima, many times local minima is not a problem. If it is a very complex surface, if even if you get stuck in the local minima, still it sometimes or most of the time it is giving me good performance. That's why local minima problem people are not using it to deal with that. But still these are the options. If you see that the local minima is very worst, then you can use these options to come out of the local minima and go towards the global minima. Okay. Now let's discuss some of the activation functions. We have already discussed in the last class 1 or 2. Let's see it a little bit more. So there are 3 activation functions we are going to discuss. One is sigmoid, tan h, and ReLU. So if you see sigmoid, the function is 1 by 1 plus e to the power minus h. Tan h is called hyperbolic tangent. It is e to the power h minus e to the power minus h divided by e to the power h plus e to the power minus h. And ReLU is maximum of the value 0 or h. So let's see what is sigmoid. Now, if you see sigmoid is passed through these 0.5. That means its value is between 0 and 1. Okay. So, what is the benefit it will give you? Now, it's bounds its output between 0 and 1. And it offers a smooth continuous derivative. So, derivative calculation is very easy here because the curve is very smooth. Okay. And it is zero center. So there is a simple decision boundary. So it will be easier for using in the classification. That's why we are using it in binary classification. What are the problem? The problem is this 2 area. That is the saturation at the end of the curve. This leads to gradients very close to 0. So when it is parallel to this place, let's say your value is going towards let's say minus infinity. So at that time, what will happen? Your gradient will, when you calculate with this simple line, it will look like a line. So gradient will be almost 0, close to 0. So if it is close to 0, what will happen? Your updation is Wt plus 1 equal to Wt minus alpha into that gradient. Whatever alpha value you take, if your gradient is almost 0, that means your Wt plus 1 is equal to Wt. Previous Wt is not going to change. So that is called vanishing gradient problem. So if your gradient it becomes 0 or nearly equal to 0, even if whatever number of iteration you do with gradient descent, your parameter is not going to be updated. But our objective is that the parameter need to be updated so that the loss will be minimum. So if the parameter is not going to be updated, why it is not going to be updated? Because due to this gradient value becomes 0 or nearly equal to 0. So we call it as vanishing gradient problem. And this is very common in text processing or rather in sequence processing. And how to deal with this we will discuss in future. Okay. So another drawback is that here the output are centered around 0.5. So as it is centered around 0.5, that's why the convergence is slower. Okay, so this is the two drawback of sigmoid, but still sigmoid is used. That's why sigmoid is only used not in the hidden layer, rather in the output layer of the binary classification problem. Okay. Also, this is another problem, that exponential calculation. So obviously in activation, if you want to calculate, again another calculation is there in for the computer, so it takes time. So this is another drawback. Let's see what is tan H. So tan H is dealing means it will eradicate some of the drawback of the sigmoid. How? Let's see. Here it has similar benefits to sigmoid, but here the output is not between 0 and 1, rather it is between -1 and +1. Okay, and the good news is here that it is centered around 0. As it is centered around 0, so convergence will be faster, whereas in sigmoid it is centered around 0.5, so the convergence is not that much faster. Okay, but still it has the same problem, that is still suffers this gradient saturation, which leads to less zero gradient, and that will also lead to vanishing gradient problem. Okay, and also it is expensive, because here we have to calculate e to the power h 4 times, sorry, 2 times, e to the power h and e to the power minus h. In that case only once. But most effective activation function is ReLU. That is called rectified linear unit. ReLU is very simple. What it is, whatever value it will get, either it will return this value if it is positive, or if it is negative, it will quash it to 0. Okay, so it convergence will be faster, and it is computationally cheaper. Why? Because d by dx is only 1. So easy to compute, because here there is no saturation gradient that is past 0. Okay, so but sometimes the problem is that if your initialization is poor, means your weight initialization, initially what we are doing, we are randomly initializing the weights. So if your initialization is poor and your learning rate is high, then there is a problem called dying ReLU. What does it mean? Dying ReLU means if all your calculation for all the neurons, because what happens after the aggregation in every neuron, this aggregation value is passed through the activation. If your activation is ReLU, and ReLU is very cheap and very good activation function to be used in the hidden layers, but there is a problem that if for all the neurons in that network, if their output after activation sorry, after aggregation is negative, then we know that ReLU will become, make all negative value to 0, so it will become 0. So if everything is become 0, then output will be 0, because nothing is going to be learned. So that is called a dying ReLU problem. So how to solve this dying ReLU? So there are different ReLU versions are available. One is called leaky ReLU, parametric ReLU, LU, that is exponential linear unit, GLU, GLU, many are there. Here I am mentioning only 3. Now you see, for leaky ReLU, what we are doing, when the value is less than 0, we are not making it 0. Rather, we are adding some typical constant value that is set to 0.01. So that some value will be there, it will not going to be 0. Another one, that instead of using alpha as a 0.01, you can make this alpha as a learnable parameter. That means along the back propagation, this alpha is also going to be learned. So that's why it is not going to be 0. And this exponential linear unit LU, it uses this. If h is less than 0, so instead of making this portion as 0, you just calculate alpha whole into e to the power minus h, e to the power h minus 1. So that's why the curve will be little bit smooth, and the derivative calculation will be also easier, and it is not going to die. Okay, so these are the different versions of ReLU. So remember what I'm saying, that ReLU activation is generally used within the hidden layers, and in the output layer for a regression task, don't use any activation. If it is a classification and you are using a binary classification problem, use sigmoid. If it is a multi-class classification, use softmax. Okay, you just remember this. Now come weight initialization. So generally what we are doing, our first step in gradient descent is that all weights in the network will be randomly initialized. Okay, so if you randomly initialize and if you initialize something which is not correct, and that will lead to dying ReLU, so that will be problematic. What you can do, we can use some systematic weight initialization process. Let's see. So how will refine this random initialization? So let's see. One such initialization process is called Javier or Glorot initialization. And generally, this initialization is used for those weights which are associated with the neuron which uses either sigmoid or tanh activation. Okay. And what it says, the don't need to remember, only just remember this, that there is a initialization called Javier initialization, and it is basically used for those weights associated with sigmoid or tanh activation of these neurons. Okay, these are the formulas. And what is fan in and fan out here? Fan in is the number of incoming connection to that neuron, and number of outgoing connection from that neuron. These are called fan in and fan out, and you can use this formula to find out. And generally we don't use this formula because for them the methods are already implemented in the framework. We just have to call them and use it. Okay, but remember this is there. Another one is called he initialization. So he initialization, it is generally used for ReLU activation. It will if those weights which are associated with the neurons which uses ReLU as activation, for those weights, instead of randomly initializing, you do he initialization, so that the initialization will be proper and it will give you faster convergence. Okay, so these are the two initialization methods. Now another concept, we call it as feature scaling. Why we need it, or do we actually require feature scaling before passing our data to the network or not? And feature scaling already we have discussed in the ML. So same thing here. So let's say I want to predict car price, and here I have to use two features. One is car age, another one is kilometer driven. And we know that car age generally between 0 to 99. It cannot be beyond 99. Well, there is no car. Of course, there is also no car for 50 years or 99 years. But still, the range is this. But for kilometer, it can be 0 to 1 lakh or 2 lakh or 10 lakh. So it can be anything. Now, if you have a value between 0 and 99 and another value between 0 and this bigger number, then what will the problem? So the problem is there is a large difference in scale which lead to slower convergence, and for that large weights are required, and which can lead to poor performance. So to eradicate that, what we will do, we do feature scaling. That means instead of use different scale for different features, we convert them into a single scale. Okay, so one such feature scaling method is called normalization, and here we call them as a min max. There are different normalization techniques are available. One common normalization technique is mean max scaling. What happens this? Now whatever is this, let's say this yellow are the actual values, and we have to normalize this value so that it will come between 0 and 1 or minus 1 and 1. So what is the formula? It is x minus minimum of this x value divided by maximum minus minimum. So when you do this for every data point, the data point will become these blue data points, from yellow to blue. All will be quashed between one scale. Okay, this is one. Another one is called standardization. So this is called standardization, means here it is called variance scaling. We will convert them the data point in such a way that the mean will be 0 and the variance will be 1. So how to do that? So for every data point, you calculate the mean of the whole data point and variance of the data point. So just subtract the mean from the every data point and divide it by variance. So all the data point will come to a normal distribution like a bell-shaped curve. Okay, and it will be better. And this is your normalization. This is your standardization. So the general rule of thumb is when to use what. So you just normalize unless the feature has close to a standard normal form, a non-normal distribution, or there are outliers. If there are outliers, what you do? You use standardization. Otherwise, you do normalization. Okay. And these transformation cannot be applied to testing data, test data. Rather, you are just to apply it on the training data. Okay. Now come to the regularization part, which is coming under model evaluation. So we need some regularization technique to overcome the overfitting problem. We know what is overfitting. Overfitting is that for my model is performing very well on the training data, but when I supply the test data, it is not giving me good result. We call this problem as overfitting problem, and overfitting problem is very common in your DL or your neural network or deep learning models. So to overcome this problem, there are many techniques available. We call these group of techniques as a regularization technique. So the regularization technique, the question is why overfitting occurs. There are different reasons. One, that the number of data points is very small, your model is very complex. Okay, if your model is very complex and you have only small amount of data point, then the model can remember every data point rather than learning anything. That's why during training, on the training part, it is doing well, but during testing, it is not doing well. So what we can do? Now we can either increase the data points, always it is not possible, or decrease the model's complexity. If you decrease the model's complexity, then the model is not that much capacity to remember, rather it is forced to learn. Okay, so there are a variety of techniques available. Some of them are L1, L2 regularization, dropout, early stopping. Let's see some of them. And most common is yearly stopping. What is yearly stopping? So now you see, when for different epochs, if you calculate the loss and you plot the loss curve, so you see for training data, this is the dot dot dash 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 line is my training data loss, and your validation loss is this one. Sometimes what will happen, now initially the training loss and validation loss is very huge, but when the training progresses, the loss comes down. But after some time, the training loss goes towards zero, but the validation loss diverges and again it goes upward. So that means it is overfitting. So what we'll do, wherever the position, in which position the divergence starts, you stop the training. We call it as yearly stopping. So yearly stopping means stop yearly. Don't go forward. Because if you go forward, then what will happen? Now your training loss is going down, but your testing loss will or validation loss will go up, and which will diverge. It is not giving me good model. So you just stop. So we call this as yearly stopping. And I will show you how we can apply yearly stopping in code. So what it says, stop training as soon as validation loss reaches a minimum. Okay, or soon after if it diverges. There is another weight regularization, we call it as L1 and L2 regulation. Weight regulation, now you see, these are the training data points. The orange color data points are training data points. And your model is so complex so that it remembers everything. That's why all data points lie on this line, on this curve. But as it is not a generalized function, if you have a black dot here, that is the new data point, and your prediction is here, which is very off. So your test data will give me more error. Okay, so how to deal with that? So we can use L2 regularization. So what is L2 regularization? Just add in some other value with the loss function. So this is my loss function. So loss function is y cap y. Some loss function is there, and we are taking average. So to add a regularization, what we do? This is my regularization parameter that you calculate L2 norm of all weights and lambda by 2. Your lambda is what? Lambda is your regularization parameter. So when you add this, your model will become less complex and it will try to not remember, rather to learn. Okay, this is one way. And generally we use it during training only, not in testing. Similarly, L1 is there. Instead of adding L2 norm, if you use L1 norm with the loss function, we call it as L1 regularization. And what happens in L1 regularization? Now it creates a sparse model. That means those parameters or weights which are very close to zero, they will become zero. And those are not, they will be as it is, or they will have less difference. So generally, this one is also used for feature selection. So if you apply, most of them, some of the features will become zero, their weights will become zero, and some of them will not. Okay, so this is another way to overcome the overfitting problem. There is another most common technique, like early stopping is a common technique. This one is also a very common technique. And remember, L1, L2 regularization can only be used if you have a small data set. If your data set is very huge and you are using generally deep learning models or neural network, so either use early stopping for the regularization or use dropout. What is dropout? So here dropout means each unit in a layer has a probability P of being dropped at every batch. That means at every training, some of these neurons will be dropped. Means they will not going to be used during training. Let's say if I use 50% dropout, 50% means out of all the neurons, 50% will not being used during training, rest 50% will be used. So that if the model is complex, if you 50% is down, then your model's capacity becomes 50% less. So it will try to, or we are indirectly forcing to learn it. So if like this, you just remove the connectors, only these things will be used. Or if for different batch, different neurons are going to be turned off. Okay, so we call this as a dropout. So the dropout probability is generally taken as 0.2 to 0.5. Okay, depending on the model, and generally dropout only used in the training time, not on the testing time. And each layer's output is generally multiplied by 1 minus pp is the probability to account for the larger signals. Okay, now we come to the last part. Question is, we have learned many things till now. Question is, what is deep learning and what is, because now till now we have discussed about neural network. Now what is deep learning? So what is deep learning? Deep learning is nothing but it is a neural network with many hidden layers, generally more than two. Okay, so deep learning is just a naming convention of neural network, because why this name came into picture, sometimes in way back, researchers who are researching on neural network, their papers has not been accepted. Okay, there are some problem with neural network that Minsky and Pepot identified, that a simple neural network cannot solve XOR problem. For that paper, most of the people leaves this field at that time, and we call this time as a neural network winter. So when people started using neural network and achieves good result, so instead of giving them neural network as the name, they give a new name called deep learning or deep network. And suddenly papers are being accepted, that's why the name came. Okay, so deep learning is nothing but it is the same neural network, but here the number of hidden layer is more than two. Okay, so generally deep learning is nothing but it is learning the representation from the inputs, and this representation will be used for the output. Okay, so let's go to the demo.
Sir, your voice is gone.
Nanchan, the network problem today. Again, you're going to die.
Is there any question? Anyone has any question on this part?
Yes, you can unmute and ask the question, then we'll go for him. Nanchan, share the screen again, huh?
Yes, yes, sir. Anyone has any question? No question. Okay. So let's go for the demo. Okay. So what today we are going to do, we will use a text corpora to classify it. using the same neural network model what we have discussed in the last class. Okay. So for that, what we need, I have to import some of the libraries. So here I have imported TensorFlow, okay, at, TensorFlow as a TF, Keras from the TensorFlow, and from TensorFlow.keras layers, okay. And from scikit-learn, I got the dataset, that is a 20 news corpus dataset, news group dataset. And these are the confusion matrix display, confusion report. These are the matrix which is going to be used for the performance measure. Train test split is required for splitting the whole data set into training and testing. Okay, so first let's download the data set. As the data set is already available within the scikit-learn's data set library, just we will fetch it. So what we'll do, so fetch this 20 news corpus data set, that I am only fetching the training part of the data set and removing all the headers, footers, quotes, whatever is there, because we don't need them. Only we need the data and its label. Okay, so let's download it from the scikit-learn's libraries. Now it is downloaded. If you want to see what is the data point, let's say train corpus data 0, this is the data that I was wondering if anyone, so this data is there, and the data set is actually have 20 labels, that it says that this question, or sorry, this news belongs to which category of news, whether it is science, whether it is space, whether it is politics, whether it is entertainment. Like these, there are 20 categories, so it is a multi-class classification problem. Okay, so now we have the data set. The data set is downloaded in the variable called train underscore corpus. So first thing, we have to tokenize it. So remember, Keras has also the TensorFlow. Keras has also this their own tokenizer, which we have already used. That is preprocess.tokenizer. But here, what I am doing, I am using Species tokenizer, because I need to pre-process the text, and in Species, the pre-processing things is very straightforward. We are not using LLTK. You can also use NLTK, what we have discussed, but there is another library called Species. So let's see how to use that. So for Specie, what you do, first you have to load the model. Let's say I'm using a small model, that is Encore Web SM. So what you do, Specie.load the model name, disable NER and parser, means we don't need named entity recognition information and parsing information, so we disable them. So now your model is your model is downloaded, that is from the Specie. And let's see this function. This is my tokenizer function. What it is doing? So the name of the function is specie underscore tokenizer. It takes the documents one by one. This document is going to be passed. What it does? What it will return? It will return the document after pre-processing. What kind of pre-processing? Now you see, for T in NLP doc, that means for every document here, for T in NLP documents, it will extract one word of that doc. And what it will do? Now it will check if that word length is greater than 2, then it will remain. Otherwise, it will be not going to be used. And the not in T dot is ponc. Is ponc means it is not a punctuation mark. If it is a punctuation mark, it is going to be removed. And not T dot is space. It should not be any space. If it is a space, it will be removed. Not T dot is stop. It should not be a stop word. It will be removed. And T dot is alpha. If it is a alphabet, then it will be used. If it is not alphabet, it will be removed. And whatever is selected, then that will be its lemma will be calculated, means it will convert it to its root form, and again it will have lowercase, converting the into lowercase. So this is my tokenizer, which will do all pre-processing, that lowercasing, lemmatization, punctuation removal, space removal, stop word removal, and other digit removal, because only alphabet will be there, rest will be removed. And also those words whose length is greater than 2 only will remain. If it is less than 2 or equal to 2, it is going to be deleted. Okay, so let's see. So this pre-processed text function I have created, it will take the text, pass this, call this specie tokenizer, pass the text, and it will return the tokens. But here what I am doing, I do not need the token itself. Rather, I will join the token by using a pipe. Why it is required? Because it will be, because we know that the species tokenizer is better than the Keras tokenizer. So that's why instead of using Keras tokenizer, we are using species tokenizer. Then we convert them into a sequence of what? A sequence of sentence separated by pipe. Then again we'll pass this sentence to the Keras tokenizer. Okay. So if you do this, what will happen? Now let's call it pre-process train corpus, pre-process text post. Just call the post for post in train corpus dot data. So all our data is present in train underscore corpus dot data. So we'll call this and pre-process it. So it will take some time. Once it is pre-processed, if you want to print it, now you will see this is my pre-processed data. What it has? Now wonder, then pipe, enlighten, then pipe, like this. Means all the pre-processing already happened. Instead of returning only individual words, we have combined them by pipe. Okay, so that now this becomes my data and it is going to be passed to the Keras tokenizer. Okay, so before going to pass through the Keras tokenizer, let's split it into train and test. So we call train test split. This is my pre-processed train corpus. Already it is pre-processed. So train corpus dot target. My this target will contain the label. Train size is 0.85. That means 85% of the train of the total data will become training data. Rest 15% will become test data. Okay. So you just sorry. Oh. So I have not processed this. That's why it is taking time. So this processing will generally takes time. Uh, Let me process it. Okay, so I'm just going through it. Once it is processed, we will discuss. So same, this process will take 2 or 3 minutes, because all these things has to be done on each line. Okay, as there are around 10,000 data points, that's why it will take 2 or 3 minutes. So once it is done, then what you will do, you will test, do the train test split. So it will be splitted into train data, validation data, train label, and validation labels. Next, what will do? If you want to find out how many data points are there, just print the length of training data and length of validation data. You will see 9,616 data points belongs to training, and 1,698 will belongs to testing. Okay. Now we'll use this data and pass it to the Keras tokenizer, which we have already done in the last class. So here the Keras tokenizer will be used for text tokenizer. So just call Keras dot preprocessing dot text dot tokenizer, and we are not going to use any kind of filter, because all kind of pre-processing has already been done. So that's why filter equal to nothing, lowercase equal to false, because we are already done the lowercasing in the pre-process step. So don't need to do that. Split. So here the split is pipe, because already in previous case the species tokenizer has already been tokenized, removed all the done all the pre-processing. Again it is combined by pipe. So when you again do the tokenization, you use that pipe to tokenize. And out of vocabulary is OOV. What is OOV? So if any word is not available during the inference or testing, that word will be converted to OOV. So that's called out of word vocabulary. So you can use any string here, but I am using here OOV. Okay. So just call the tokenizer. So tokenizer will be called. Next, this tokenizer will be fit on your training data. So what we will call tokenizer dot fit on tests. So tokenizer dot fit on text method will fit my tokenizer on the training data, and all these processes, whatever is defined here, will be converted, and a list of vocabulary will be created. That means the tokenizer will create a list of vocabulary with their index, and your OOV is your fast index. Index 0 is OOV. Rest all the words will have their own indexes. Okay, so if you see, already I have previously done it. So let me show. These are the this is, let's say this is my word and this is the index. Okay, so OOV, where is OOV? Just a minute. So if you see, so many vocabulary are there with this corpus. So here you see index word is one is OOB, two is no. So these are the index. OOB is one. And how many vocabulary is there? So there are actually 45,000 vocabularies are there. Means 45,000 words are there. Okay. So here you see 45,000. So now, sorry, 45,395. This is the size of vocabulary. So what we have done? We have pre-processed our data points through specie, then combine them with the pipe. Then we got the sentences with the pipes. Then we call Keras tokenizer, because without Keras tokenizer, we cannot pass the data to the Keras model. So we call the Keras tokenizer, and using that pipe to create the tokenization, do the tokenization, and it creates the vocabulary. And there are 45,395 vocabularies, and out of what is OOB. Okay, so let's run this one. Already it is over. Let's run it again. So it took 4 minutes. So this is the case. And now you do the train test split. And if you see, there are this many number of training data and testing data. And we are calling the tokenizer. So tokenizer is called. Now it is fitted on the tokenizer. Okay. And if you see the configuration, it will show all the values of the tokenizer. Okay. So it will take time. So now this is, and if you print what is the vocabulary size, it is 45,395. Okay. Now let's do the vectorization. So now my tokenization is over. Let's do the vectorization. So we are using the same vectorization principle which we have discussed. Either we can use one-hot encoding, or you can use bag of words with frequency counts, or you can use TF-IDF. Okay. So for creating the vector of each word, what we will do? We will call this function. What is that? The tokenizer dot text to matrix. So if you use tokenizer dot text to matrix, what it will do? It will convert it into a one-hot vector. Or if you use mode as a TF-IDF, then it will be converting into TF-IDF vector. So let's see one example of this. So if you see, this is one example I am taking, and when you convert them, what will be the size? Size is one vector, and how many columns are there? Now the number of vocabularies. Here we have 45,000 odd vocabularies, so all are zero. Only those positions which contains these words have one. Okay. And if you want to see which positions have one, so this is going to do that. So these are the indexes 3, 27, 32, and this is the original sentence. Okay. And if you want to use TF-IDF instead of binary or your one-hot encoding, just call the same function tokenizer.text to matrix, but pass TF-IDF. If you pass TF-IDF, so instead of 0 and 1, it will give you the values. Okay, so TF-IDF score is given. Okay, so for simplicity, let's use the same one-hot encoding. So for one-hot encoding, what we'll do? We'll call tokenizer.text to matrix, pass the all training data, and to represent in a dense form, we have a tf.sparse.from dense. Just pass this output to this one, so it will create a X train. Now my X train is a dense representation of my vector, which is converted using one-hot encoding. Okay. Now, if you want to see, let's complete it. If you see what is its shape, the shape will be 9,616, because these many data points are there. Each data point vector size is 45,396, because for each vector, the number of vocabulary is this much. That's why the vector size will be the size of the vocabulary. Okay. Session is crashed. Okay. Let me rerun it. Oh, we have to run it again. So I'm not running, it will take time because it is saying that you have to rerun it. Okay, now what we'll do, we'll print the labels. Okay, so let's print the labels. So when we print the labels, just see, this is the function to print the label. Just a minute, just a minute. It's not visible to me. Okay, okay. Okay, so here print your train label. So just it will print it. Okay, and now X train is already created. Now we create the Y train. Now the question is, for Y train we have the labels. Labels are only these values 2, 3, 4, 5 like this. The number there are 20 possible classes. So each class has a number. So but we need, as it is a multi-class classification problem, the output will be softmax. Okay, so that will get vectors. So already we have discussed in the last session that the labels must be converted into one hot vector. So there is a easy way to do that in the keras. Just call keras.utils dot to categorical, pass the labels. What it will do, it will convert all the label into one hot vector. Okay, and this is one example that you see. There are 9,616 examples, and each is converted into 20 size vector because it is one hot vector and there are 20 classes. So each vector size is 20. Now see, if you print one vector, one label, this is the label. Only this third position is 1, rest are 0, and the class is Windows miscellaneous os.ms. This is the class label. Okay, so now what we'll do, once it is there, you convert them into the validation data also need to be converted into dense format as well as into categorical format. You just do that same thing. Now your data is ready. Now what we have done on the data, we have downloaded the data, we have pre-processed the data using specie, then combined with the pipe, then we pass this combined pipe data to keras tokenizer, which creates the vocabulary, and then we call text to matrix of this tokenizer to convert them into one hot vector, and the label is converted into one hot vector by using two categorical. Also we have converted the validation data in the same way like we have done in the training. Now it's time to build a model. Okay, so to build a model, what we'll do, same thing, you use keras sequential API. Just call keras.sequential. Within this you pass the layers. What layers we are going to use? Now we are using two dense layers, and here norm units means 128 units. So layers.dense, this is your 228 directly. Sorry, 128, you can use 128 neurons. Activation I am using relu. This is my initializer. Okay, so here this initializer, why I am using random seed as 1, because every time if you run, the same output will come. Okay, so this is my initializer. So and the output dense layer will have number of classes. So we have 20 classes, so this norm classes will be 20, and activation will be softmax because it is a multi-class classification. That's why it is softmax, and the hidden layers has relu. Okay, so if you see, uh, this is my model. Okay, my model is ready. Now after model is ready, what you do, you compile. So the model.compile method will be called, and for compilation we have to pass the optimizer, we have to pass the categorical cross entropy as the loss function. Why? Because it is a multi-class classification problem. That loss function will be categorical underscore cross entropy, and the metric what we are going to use is your accuracy metrics. Okay, so that we have used. Now once your model is compiled, all the necessary things are provided, then we have to train it. So how much we are going to train? Now we are going to train for 15 epochs, and here you see batch size is 128. So batch size is 128 means it will take only 128 randomly sampled data from the 9616, and each batch contains 128. This batch by batch will be provided during training, and accordingly the updation will be done, and the process will continue. So here you just call model.fit, then xtrain, ytrain. These are the training data and the training label. Epochs is 15 and batch size is 128, and you pass the validation data. Okay, so it will going to process. Okay, so once training is done, then what you do, you have your training history. So this history will contain all the training results, means all the loss, training loss, validation loss, training accuracy, validation accuracy, everything is there in the history. So you can use that history to print. So here, what we are doing, we are collecting the history of loss, that is training loss. This is validation loss. Similarly, accuracy and validation accuracy means training accuracy and validation accuracy. You got this, and you just plot them. Okay. So just a minute. Let it be. Just I have rerun it so that you will see the output. Just a minute. Till now, it is okay, or is there any problem? Or that in pre-processing it is taking time? Just a minute. So once you see, once we run this, your training is done. Now you can print the all the accuracy versus training core. Sorry, training accuracy versus validation accuracy, and training loss versus validation loss. Once we do that, then I will proceed to show how to use your list topic. Just a minute. So during that time, if you have anyone has any doubt, please ask. No doubt. So it will take another 50 60 seconds. Yes, one message is there. Let me see. Okay, okay. I'll this slide. Are you talking about slides? Okay, okay, okay. Let me see. Because the things are already available in YouTube, so you can check. Okay, let me see if I can share. I will share it. Don't worry. I will share. Any doubt on this part? Okay. So now it is completed. So you see, just see the diagram. So already we have trained it. Yes, this training process is continuing. You see, training process is continuing now. In the during training, this is the accuracy and loss for the training data. And once one epoch is completed, on the validation data, it is showing the validation accuracy and validation loss. So you see here, for the first epoch, training accuracy is only 26%. For the second epoch, it becomes 59%, and it is increasing. Okay. Oh. Or let me share it again.
Yes, yes.
So this training process is going on. But one thing you notice, you see, the training accuracy is increasing. It is now 90%, 93%, 94%. But you see, the validation accuracy is not increasing. That means the model is not learning means general things. It is not learning, so it is overfitting. Because when it is overfit, now when the training is good, means training accuracy is increasing, but the validation or test accuracy is not increasing, or it is decreasing. Okay, or indirectly I can say the loss is here in training loss is decreasing, but the validation loss is not decreasing that much. You see here it is 0.13 but here it is 1.60. Okay, so that means clearly the model is overfitting, it is not learning properly. Okay, so to deal with that we will discuss something. So this is 14 number, epoch number 14. Now after 15 epochs, you see the training accuracy is 96%, but the validation accuracy is just 65%. That means it is not as good as the training accuracy. That's why it is called overfitting. Now when we plot this, you see this is my plotting. So your training accuracy, this dot 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 is your training accuracy, this line is your validation, sorry, training loss, this validation, this is called validation loss. Now initially the training loss and validation loss both are decreasing, but after 1 2 3 4, after fourth epoch it is increasing. Okay, so as it is increasing, that means if you stop here after 15 epoch, whatever model is learned, that is not a good model. So what I can do, I can stop early. So stop early means instead of stopping early, once one thing you can manually do that after training 15 epoch, you get to know that after 4 epoch it is diverging. So you just train for 4 epoch. Okay, don't train for 15 epoch. This is one solution. But always it is not possible. That's why we will use early stopping. So let's see. So I am using the same model, same structure, but here the number of epoch I am using as a 4, because number of epoch is 4. So when it is trained, so you see it is 81% and it is 65%. So somehow it is diverging, started diverging, but we are stopping there. Okay, and when you see the model dot summary, you will see model dot summary will give you what are the number of parameters. Now for the first dense layer, the non is your batch size and 128 is your set. Okay, means 128 neurons are there in this dense layer. And how many parameters? These are the number of parameters. The parameter calculation is very easy. If you want to calculate, I have given this here. What is the number? How will calculate? Here the input is for 45,396 in the input. The output is 120. Sorry, the intermediate layer which contains 128 neurons. So you just multiply this plus into 128 plus 128. You will get this value. So these many number of parameters are there. These many weights are there. Okay, and if you want to see any one weight, these are the values of the weight. Okay, after training. And let's see that how we can reuse this instead of using manual stopping. Here what we have done, manually we have stopped at fourth epoch. Can we use a yearly stopping? So how to use yearly stopping, let's see. So this is, there is another model I have created, same model, all these okay, let me complete this one. Yes, this one is for pre-processing for your test data. So this is my training data. On training data, we are quite sure that it is overfitting. Let's do for testing. So you collect the test data, download the test data, do the same pre-processing step on the test data. Then you convert them into dense format, and your output will be converted into one hot format by using two categorical. So that's pre-processing. Again, it is taking some time. Okay, now it is over. So now you evaluate on the test data. So model.evaluate will evaluate on the test data. You pass X test and Y test, so it will give you result on the test set. The model is giving 60% accuracy. Okay, and if you see the loss, test loss is 1.38 and test accuracy is 60%. Okay, and if you want to predict, so the same thing, this will give you the prediction value. This prediction can be used for creating confusion matrix. So to create confusion matrix or any such metric what we have already imported, call this one that confusion matrix, where it is, just see. Yes, this one. So here, what we are doing, we are just applying the softmax. So the softmax value is this. So here you see the confusion matrix. Call the confusion matrix, pass the target, original target, and the prediction, and it will display. So just display it. So there are 20 classes. The confusion matrix will be 20 by 20. Okay, and you see many misclassifications are there. Only these diagonal are correctly classified, means this shows the correctly classified number of data points correctly classified, and those other values which are there, they are misclassified. Okay, and you see more in rake motorcycle class, most of the misclassification are done. That means your model is biased to this. If it is not finding any class, so it is just to say that it is a motorcycle. Okay, that's why this strip contains all values are present here. It should be 0. Okay, so and this is your classification report for for every class. The precision recall and F1 score is given, and overall accuracy is here, and this is the macro average. That also you can get from the classification report. Let's see, just I'm ignoring this part. Let's go for the just let me see. Yes. So let's take another attempt. Here what we'll do, we will again reprocess it. So we are just pre-processing where the minimum, if your data set contains, or your any data point contains less than 5 tokens, it will be discarded. Okay. So that pre-processing step we have done. All other pre-processing step is same. Okay. So I'm directly going to the model part. So just see, where is my model? Yes, this model. So you see here we are creating a callback. This is called yearly stopping callback. What I have created, I have created tf.keras.callbacks.yearly stopping. So yearly stopping method is there. Just call that yearly stopping. Monitor validation loss. That means during training, it will monitor what is the validation loss. And if your validation loss is going decreasing, it will do nothing. It will just go on training. Okay, it don't automatically, it will go on training. But when your validation loss diverges, for patience parameter is 1, means for one epoch, if it diverges, means it increases, it will stop. We call this as yearly stopping. You can, if you give it a 2, so it will go for 2 forward epochs. It will check for 2 consecutive epochs. If it is not decreasing, then it will come back to this original place and it will stop there. So just when you are training, you just call this. So here callback, you just add ES callback, because ES callback is the variable which contains this yearly stopping callback. So what it will do? Now it will go on training. Whenever your validation loss increases, it will stop. So now you see all these validation loss are decreasing. After this, perhaps it is increasing. That's why it is stopped here. Because you see, number of epoch is again we have given 15. The same 15 epochs are given. Okay. But it stops yearly. Why? Because yearly stopping principle is that once it start diverging, it will stop. Okay, so this is the best way. Instead of giving manual value, that is 4 or 3, you just use this callback as early stopping. So it will automatically stop early before the divergence starts. Okay, and if you see after this training, you see the motorcycle which was previously many values are there. Now it is 1-digit values. Okay, that means it's learning perfectly. Okay, and your precision is also, sorry, accuracy is increasing from 60 to 68%. Is it okay? Now you can have this function. So here this is a function what we have created to, if you get a new data point, how you will classify it. Your model is trained, your model is present in what? This model name. this model is name is what model underscore next. So this model is already trained. We can use this trained model to give new data point and find out what is its class. Okay. So for that, we create a function. Whatever new post it gets, it will tokenize it. It will use the model next predict, then find out the maximum argmax, because it is going to give you a list of probability. So it will find out which class has highest probability. That class will be returned. Now, once let's say this is my one text. When I pass it this text to classify post, it says that 98% probability is that it is SciMed and James Webb space. So you see, when it is passed, it says correctly classified, that is belongs to space, because this article belongs to space. Now your class made in the last 10 years with 4-speed manual transmission. Okay, so this gives me auto, because car belongs to auto. Okay, this project is awarded by ATT in 85. 5 of its pins were used. So it is something called something about your electronics. So when you run it, it is correctly classifying that it is electronics. Okay, so in this way you can do this. So I have given some additional material. You can just go through these tutorials if it is you are interested. And I have given you another practice problem. So here you have a data set in TensorFlow Keras data set that is called Reuters. So there are 11,000 Reuters news article with 46 categories. This one we have done for 20 categories. There is a 46 categories. Just create a model like we have created in the above part, and fill up this and learn, train a model and find out what is the output. Okay. So from my side, this much. Is there any doubt? Just ask. On this part, is there any doubt? Very simple. You have the data set, tokenize it, then convert them into vector. Either you use TF-IDF or one-hot vector, and in next class we'll see what to vectorize it, then split it into train test, then create a model, okay, using dense layers, then compile it by passing the optimizer, loss function and metric, then fit it on the training data. If a callback is required, use early stopping as the callback, and your model is trained. Once model is trained, you can predict on the text data, or a new data if you get also, you can predict using the predict method. Okay.
You first run whatever code is going to be shared. Okay, first run that one as it is. Then if required, you can change the data set. Okay, first run this one and try to understand each and every statement. Fine, whatever things, because once you run the same program, you will get the confidence to run other. Okay.
So I have already given a new data set in the last part of this notebook. So similarly, you try. If you first go through the first part, just watch. Already I have mentioned what is there. I mean the markup I have given every instruction. So easy you to understand, and then you try the Reuters problem. Okay, Reuters classification problem.
Your understanding is not enough. You have to run yourself. Then only you can face the problem. You have to solve that one. SAR is running. Okay, we got it. Okay, we can run. No, that's not the case. You have to run. Then only the things will be clear. Okay. Okay,
Once
then I
you go
think
through
tomorrow
the-
there will be no class, Nan sir. Again,
Yes.
we'll meet on Monday.
On Monday.
Another 4 class will be there. Then we have a break of like 10 days, you can say. See, 5
Yes,
days
sir.
for the workshop. Another some 3 to 4 days for this Roger, all those things. Okay, again from 15 onwards we'll start. Next
Okay,
week there
sir.
will be 4 class. Okay, after that only they will attend the workshop. All will attend. Then only again 2-3 days break. Then again from the 15th we will start giving the mini projects.
Yes, sir. Yes.
That we'll see. Okay, then thank you very much. Stop here.
Thank you, sir.